You just get a video. That works.
Cool. I can even
Oh,
see
you're
people.
using YouTube to record it?
I'm using anything I can get working. I'm not very picky right now.
Actually, I didn't know there was a feature on YouTube for this.
I tried the Hangout, but
Just uploads directly onto YouTube.
yeah,
Oh.
onto our channel.
That's pretty cool.
Yeah, there's a way to do a Hangout on air, but I couldn't get it to work. You know, I clicked on OK and it never went to OK. It's like said you have to verify my account. I verified my account. It didn't allow me, so
That's weird.
Okay,
wait
we
a
begin.
minute. Yeah, let's do it.
We're missing one guy. There he is. So, part of this talk is to introduce some of the basic concepts in electricity distribution. We talk a lot about power factor and so forth, power factor correction. Just wanted to provide a high-level overview so that everyone's kind of on the same page and can reference it from a high level. Of course, I don't go through all the details, but at least you'll have a basic understanding. Okay. Next slide. Next slide. Cool. So before getting into any of the technology, I wanted to do a little bit about a history of AC and DC. There's a big misconception that Tesla was the father of AC. It's not really true. So, what's that? So there was a lot of development from numerous people. The first generator was actually developed, or alternator was developed in 1835 by Hippolyte Pixii. And then Faraday and Henry had actually done some testing themselves. The problem is that was never adopted because when you run an alternator, you also need something to use the power, right? And the number one application was industrial motors. So they had no functioning motors of AC that could utilize this alternating current. So people were doing different scientific testing and building different components around AC. Then the decade that really brought AC into the forefront was the 1880s, right? And there were a number of different contributions that happened. In London, England, Sebastian Ferranti and Lord Kelvin, who were working with Siemens at the time, showcased the first transformer design, like functioning transformer design, being able to step up and step down. Then in 1884, Lucien Goulard actually implemented a 25-mile long lighting system. I think it was for some type of rail car, or streetcar system. And that was actually using step-up and step-down transformers to distribute AC for lighting. And they were using, and he was using Edison's DC light bulb, right? Then in 1885, Galileo Ferrari began work on the first polyphase AC motor. And at around the same time, in the same year, George Westinghouse started looking at AC. He bought an AC generator and he bought a Goulard transformer and had his engineers start looking at implementing an AC system, right? So 1886 was a big year because in Great Barrington, Massachusetts, they actually implemented a first AC power system using step up and step down in the US, right? And it was mostly for lighting, obviously. The same year, Buffalo, New York, they actually implemented the first commercial AC power system for lighting, and that was obviously using Niagara Falls, running alternators. And in the same year, Nikola Tesla actually attempted to sell his AC power for lighting system to New York City, but New York City was way too heavily invested into DC at that time. So then 2 years later, while Nikolai was also doing other things, he actually showcased the first AC motor, right?
Polyphase motor?
Polyphase motor. right?
More than one phase?
More than one phase.
Wow.
Right? So, and then they had a number of lawsuits with Ferraris because Ferraris was also had some patents, and Tesla was saying that he conceptualized the idea before Ferraris, and there was a whole lawsuit. Anyway, this is what led Tesla to become famous, essentially, because George Westinghouse went out and bought Tesla's patents after he had settled the Ferrari stuff. And so in the U.S., George Westinghouse was the first company to start implementing AC power and be able to distribute it to industrial consumers for use with motors. By the 1900s, another interesting point there is that the Tesla AC motor was a two-phase motor, right? It wasn't a three-phase system. So then other guys came along and implemented the three-phase system, which was actually more efficient because of the coil windings and so forth. And then by the early 1900s, three-phase had become the principal power source.
And we are using the technology that is more than 100 years ago right now.
Yeah, I mean, it hasn't changed. A lot of other concepts have been developed around the system, and we'll get to some of that, right? So what actually happened was that the early adopters of electrical power grids were actually implemented in DC, because DC was well known, right? So you have a generator and a motor, and the generator and motor are actually interchangeable, as I will show. And there's no difficulties with regards to capacitance, inductance, and all these other things. So it's a relatively straightforward system, right? The problem with DC is that there was no efficient way to convert it from high voltage level to low voltage level. So when you have a DC distribution system, when it goes down to the consumer, you need a low voltage so that you don't kill people, right? So what was happening was that you had to create power generation stations within small locations, and it was getting like really dirty, right? It's not, you can't put a coal-fired power plant in a residential neighborhood of like 300 homes. It doesn't make sense. So, so AC was not utilized actually until the AC motor came out, because this was kind of the stumbling block, right? A big consumer of electricity are all the industrial plants. So DC was available, AC, yeah, it's great, doesn't make sense because we needed to power manufacturing facilities. When the AC motor finally came into production, it was essentially a game changer, right? And of course with AC now, because you had step-up and step-down transformers with low losses, so high voltage, you're able to use less copper with less current to transmit the same amount of power. And you can transmit it over much larger distances, and therefore you can make large power plants for electricity in one specific location and distribute it everywhere, right?
So the industrial areas were using DC motors for all their stuff. So that means they have to have a coal fire within their...
Not within, but close by somewhere, right?
I think they want to fight between others and Tesla, right?
Yeah, I mean, that was in New York City.
Right.
Tesla had a little bit of a grudge against Edison because he used to work for him. The story goes that Edison asked him to fix some problems in one of the DC systems and challenged them. And Tesla actually, he told Tesla that if you can fix this, I'll give you $50,000, which is a lot of money back then. So he fixed it, he went into his office, and he said, well, I was only joking, you're not used to American humor, right? And that's when he quit. Right?
Kind of sounds familiar.
I never offered $50,000.
I'm
So-
not talking about. I'm not talking about our company.
Oh.
It's having seen the industry a lot.
So a little bit about DC basics, which will help us understand the AC stuff. Everything is based on the DC motor in terms of generation. So you have two magnetic field currents. There's something called the right-hand rule. Whenever current flows through a conductor, right, it generates a magnetic field, right? And an electric motor, so this is the schematic, and this is the actual physical unit, has what's called a commutator. The commutator spins around, and you're able to create a magnetic field across the rotor, right? So, using two magnets opposing each other, so you have a south and a north, then on the commutator, if you apply a DC voltage, this loop of copper will actually generate a magnetic field that's perpendicular to the magnets. Okay, that's the fundamental principle. And then the two norths will oppose each other, the two souths will oppose each other, and the north-souths will attract each other. And that's what gives you the spin, right? It's a very simple system to begin using. All the math is based on vehicles IR, essentially. There's modeling associated with the DC motor, but we won't get into it. The motor and the generator are equally the same. They're one and the same in terms of their functionality, right? So you can apply voltage here, and you'll get spin. If you spin the actual rotor, you get voltage on the output. The problem with these guys is that they're relatively high maintenance because of this commutator, right?
Brush.
The brushes spin around. There's copper connections. The brushes actually contaminate the commutator rings, and then your motor starts to fail quickly. So, how is it done with AC? Well, if we take that north-south principle on AC, we use the same type of loop. We can add, instead of a commutator, what are called slip rings. And one slip ring is attached to one side of this coil, the other one to the other side. And as you spin this, then what happens is an AC waveform is produced in this coil, right? That's the equivalent. So, I mean, there's multiple steps there. So AC becomes very easy to produce with this model. The problem with AC then becomes, once you have a particular frequency out of one generator, every other generator that has to jump on that system has to be synchronized with it, right? Which is a little challenging, but it's not impossible for the time to do. And then the math becomes much more complicated, right? So now you have to deal with resistance, inductance, and capacitance. And we'll get into that in a little more detail later.
But you still use the brush, right?
No.
No?
No. I'll explain. So now there's... Yes, sir.
So in today's world, would a DC power distribution grid make more sense than an AC, or is it still...
We'll get to that.
Okay.
We'll get to that. So that's a very good question, by the way. And we'll get to that.
Good.
So, as I said, by the 1900s, three-phase dominated, right? So similar to the previous slide, now what we do is we actually put a magnet in the middle, and the magnet becomes a rotor. So this is called the field coil. You energize the field coil, so you get a north-south, and you rotate this guy using a steam turbine, for example, and you have three coils which are 120 degrees out of phase. This becomes your three-phase system, right? And in a 360-degree turn of the unit circle, you get three phases which are completely equal. and sinusoidal, of course. So if you Google transformers, that's all you get. But seriously.
You get some cars too.
Oh, it's
on
sad.
Like the
I just got
Chevrolet.
Sad.
I got the movie. Anyway, so that generator is the basic building block for generating power. Then what's important in the distribution grid is being able to step up and step down the voltage. And this is done very simply with a magnetic core, where you wind some copper around one side, which becomes the primary. You wind some copper around the other side, and this magnetic field, which is energy, from one side is transferred to the other side, right? So you have primary and secondary, and it's a very simple relationship after a lot of the other mathematical calculations. It becomes a ratio of the turns, the voltages,
What do you mean by real DC transformer?
as opposed to the
Oh,
moving.
okay. Mhm.
So similarly with the three-phase system, you have essentially a core with three legs in it, and you wrap one of the primaries on each leg, right?
Yeah.
You wrap the secondary on the same leg as the initial ones. Now this is where it gets interesting, because these connections allow you to tap and either set either a generator, transformer, or motor as a Y or delta, which all of you guys have heard but probably are a little bit confused about, right? So if I want to set this as a Y, what I would do is I would connect the V1 bottom to V2 and V3, and that creates my neutral point. Alternatively, I connect these points from here to here, from here to here, and from here to there, and that becomes a delta, right? So it's just a matter of how you do the connections in the transformer. And then on the other side, you can do a delta to Y or a Y to delta any way you want, with the same relationship. Okay?
Why? What's why?
Yeah,
It's a connection, what
Yeah,
the
it's just a
vibration.
connection, and I have a better description here. So any generator, transformer, or even motor can be wound in either a delta or a Y, right? As I showed previously. So a delta, essentially all the inductance coils are connected in this fashion. A Y, they're connected in this fashion, right, with one common neutral. On deltas, the majority of high voltage stuff that gets transmitted is usually a delta connection, because then you don't need to send this neutral wire, right? Because you're not using it for the most part. And there's an advantage to winding motors as deltas, because if you lose one phase, or if you lose one winding, the motor continues to spin. Whereas in a Y, if you lose one winding, the motor actually abruptly sort of starts to vibrate, right? And it shakes and stops. Right?
Why is that?
The reason is because these two coils, so if I lose this coil, right, these two coils only see A, C, and B voltages, right? But if I lose one coil here, these two coils still see A, B, and C, right? So the motor still has more power. So a general grid today looks something like this. And you start off with the power station. The power station, regardless of whether it's coal, nuclear, or natural gas, will use steam turbines to turn the alternators or generators, which we use interchangeably. That will usually produce anywhere between 2.3 and 30 kilovolts. Then you'll go to a power transformer, and that will step up to the system between 120 and 765 kV. Huge amount of power. From there, you'll go to a transmission substation. So that will be a step down to 69, 115, or 138 kV. And then that will actually get sent to a distribution substation, which will be 3.3 to 25. So at this point, you go either to factories or you go to residential consumers. At the factories, these guys usually will pay the utility for a particular voltage that they require. Sometimes the substation will actually be owned on premises by the user instead of a utility, and sometimes the other way, depends. And then from here, these little pole transformers or the transformers that are in your ground, they produce your 120, 220, right? And another note here, which generates a lot of confusion, every house only gets 2 phases out of the 3, right? So what they do here is, if you have a set of 30 houses, right, they're going to split up 10 houses, 2 phases, another 10 houses, another 2 phases, and the last remaining 2 phases on the other 10 houses. So they try to balance out the system.
Do you even get 2 phases?
Yeah.
Because I thought they call it actually single phase in the US.
It's single phase, but it's phase to phase, right?
Because it's just as one coil just split in half, correct? So you would, if you take both, if you take both hots, it's 240, and if you take the neutral and one hot, it's 120, isn't it?
Right, but that's a phase to phase actually in the transformer.
Because I think they do call because I bought a sub panel and they clearly say they call it single phase.
It's single phase coming in, right?
Yeah.
But it's actually at the transformer, it's a 2-phase going out, right? That's how the tapping works, right? You can also have the transformer tapping in the middle of each phase, potentially, like you said, but I don't think they do that. I think they actually balance it out that way. It's a matter of semantics, right?
Yep.
So is there anything in the household that uses 2 phases?
Yeah,
Washer,
Dryer.
electric car charger, typically any, because the same thing holds true with the wire. The amount of copper that you would need is higher, and so for the things that use just more power, they typically put it on 240. And then in Europe, everything is 240. Probably Canada too, isn't it?
No, 120.
Is 120?
We have the same here.
Oh, okay. So Europe is 240, and then if you you would actually get to that.
We just have a slightly different distribution for industrial application. We use 600, right, instead of 480. That's it, right? So
130.
So those are the basics of AC. Now, high voltage DC systems getting reintroduced into the world. Why? Because of power electronics, right? The advent of power electronics actually allows relatively cost effectively to be able to take high voltage DC and convert it down, and to also go the other way, take low voltage DC and convert it to high voltage DC, right? So there are advantages with using high voltage DC systems because there's no synchronization required, right? So if you have a lot of windmills and solar panels, you can just add them all to the DC system, and you don't need to do phase control and all this, so your converters become much more cost effective.
How do you convert voltage? You pump it down. What kind of technology?
Buck boost converter, right? Very, very simple. So they have high voltage IGBTs. They vary 1 to 2 kilovolts. When you get into the higher voltages, you actually put all those guys in series, right? And you control them. So you can, if you have a 1 kV IGBT, for example, or a MOSFET, you won't get a MOSFET, you'll get an IGBT. Then if you have a 3 kV system, you're going to put 3 or 4 of these in series and control them on and off. That becomes the total voltage of the system, right?
Well, they can sustain that kind of low voltage level?
Yeah.
So for a 500 kV system, that means you have a shitload of those?
Yes. Yeah, they use like thyristors and different other devices. I'm not updated on the latest technology, but yeah. So they're a little cost prohibitive, obviously. I know a guy in Toronto, he actually manufactures high voltage IGBTs. One IGBT handles a couple of thousand amps, about this big, costs like $3 grand, right? So,
Do they use some kind of a ultra cap in order to do the boost converter?
I don't think so.
No?
Just regular caps.
Really?
Yeah.
You do that?
Yeah.
Okay.
So the other advantage is that with DC, you can attain much higher voltage levels. So there's stuff being done around the world at 1 megavolt plus, 1.3, 1.4, which is significant. In terms of the transmission lines, it becomes much more cost effective because now you only need potentially one wire to transmit in your DC, right? So you can, in this system, what they do is they'll have like a plus minus 500 kV DC system, and then they use earth, the actual earth as ground as a returning path, right?
Wow.
So that becomes a 1 volt. The equivalent is something like this. They have better designed towers today, but it's still a lot more copper, fundamentally.
In that kind of dangerous, I mean, if the grounding is not perfect, you can get
Well, but
it.
it's always earth, right?
Oh, but the
But
Earth
so
would
they
have
have-
different potentials.
Right, it's
Yeah.
not just 0 to 0, 1, 2, 3, 4, 5 to
Right.
10,000.
So where they actually do the grounding in a lot of these high voltage distribution points, it will actually, gate off, essentially close off a large section of where those ground electrodes are, because you will get voltage potential in a particular area,
Yep.
right? So they're very cautious about that, but it's doable, right?
So
And-
who is doing that now?
a lot, like Siemens, ABB, all those guys, there's different.
But who deployed such things?
First, who deployed it first,
Oh,
for example?
deployed anyway?
Yeah, absolutely. Probably the majority of wind farms, when you see like 100 wind farms somewhere, the majority of them are actually probably connected to the grid through high voltage DC, right?
Yeah.
So that's
makes sense for that.
that's the typical application, right? Because you want to put a wind farm up in the mountains and there's no grid to connect to. So you have to pull transmission line. Now you have to do the calculation, how far is this transmission line? How much real estate do I need fundamentally to do it in AC? How much real estate do I need to do it in DC? How much is it going to cost me, all the components? And you figure out your ROI and you say, okay, high voltage DC is the way to go, right? And there's probably some engineering trade-offs associated with that. It's not all cost driven, but that's typically what it's done,
The
right?
wind probably like 5% of the power generation, right? At most.
Today, yes.
So solar and other renewables energy were in Germany at 60%.
That's very impressive.
So
That's very impressive.
Germany's not very sunny. So I think
But
it's going up.
I think the most part is still the nuclear, right? The most part is still the nuclear. in
Coal.
Germany.
No, the 60% was only renewable energy.
Well, Germany set out
Because
a
they're trying-
mandate to
yeah.
shut down all their nuclear power plants.
They're
right?
shutting it all down.
Because they were at like 20% or something.
You know, I actually don't know. But they had a few.
Yeah.
Of course, now they're buying it from France, who runs quite a few reactors, and from the neighboring countries, and it's back
Well,
to
it's
coal.
okay,
so
right?
but,
If it blows up, it's on France's.
Yeah, it would never come over the border. I mean, obviously the
Obviously.
fallout knows where
Right.
the border is.
I mean, so 6% of the power is generated in Germany, or 6% used in Germany. The two things are very different, right?
I don't think the others have really a very high concentration of renewable energy. It's not like they imported 59% from
60% of
France.
their power is
No, I'm saying they maybe like 90% of power from other countries to Germany, and
No,
Germany.
it's 60% of the consumption.
Consumption. Right?
Of the consumption was renewable. So
That's very impressive.
yeah.
How renewable meaning wind and also
Wind and solar, right?
Yeah.
That's it, huh?
Yeah, most of
Water.
Yeah, there's.
the dam. Right?
I'm sure there's something that's probably not They did a lot of incentives for people to put solar on their roof.
Okay, so let's go back to some AC basics. So you have your alternating power source. The three elements that are fundamental in any AC system is a capacitor, an inductor, and a resistor. Essentially, you model everything with those three elements, right? What's important to note here is that capacitors have current which is leading the voltage, inductors have current that lags the voltage, and resistors are actually in phase with the voltage. And this is very important because if you set a capacitor with in parallel, if you connect the capacitor to an AC source, essentially you'll just be bouncing power around. It's all kVAR, and we'll get it to the next slide, right? So these are the basic elements. Resistors are the only ones that actually do real work. And so there's a beer analogy for kVAR, right? In that the kVAR is like the head. It doesn't really do anything. It's power that's used in the system. Kilowatts is the good stuff that you drink. And the whole glass is your kVA, right?
What does the R stand for?
What's that?
What does the R?
Reactive. Volt-amps reactive, right? So whenever you see that, it's volt-amps reactive, right? So a typical power formula, if you're not looking at the actual full waveforms, is your VRMS times your IRMS times your power factor, cosine alpha. That's the phase shift, right? Which I had.
That's the angle between the voltage and current.
Yes. So the power factor is the actual angle between voltage and current, right?
You had some fun with that slide, huh?
So in the power calculation, real power is actually voltage, the full waveform times the current waveform, right? And when you look at an inductor, it's interesting to note that if we multiply this section here where the voltage is positive and the current is negative, we get a negative power, right? If on this side, both voltage and current are positive, where we get a positive power.
But how can power be negative?
Mathematically, it's negative. So what it means is the power is actually exiting, right? So in an AC system, voltage and current go forward and backwards, right? Alternating, right? So when you have power that's forward, negative and positive, what it means is that you send power to your inductor and the inductor sends power back to you. That's volt-amps reactive.
Oh, okay.
Right? So you essentially have power that's bouncing in the system, causing inefficiencies, right?
Or transform a vector into a parameter.
Yeah, I didn't want to get into like the whole vector analysis stuff, right? This is easier to understand in my opinion. So then if we look at the resistor, the voltage and current align in phase, right? You'll notice positive with positive current generates a positive power. Negative voltage with negative current creates a positive power, right? So mathematically you always have to believe, you know, the math and the science, right? So, in terms of what is on a typical grid, in terms of who uses, who are the consumers, we have the whole grid section as a generator, we have the substations for transmission and so forth, but at the end we essentially have resistors, motors, right, and then switching electronics. Those are all the loads encompassing pretty much everything that the world uses, right, from the electrical grid, right, simply put. So what happens when you have a switching electronic? Well, this is the simplest form of taking in an AC signal, an AC power source, converting it to DC using a rectifier, right, and then doing some stuff on the other side. So this rectifier will actually rectify that AC like that, right? And what that does is that will charge this cap to create a DC link fundamentally, right? Providing power to the rest of the system. That DC link will use a current which is not necessarily in phase, and definitely not sinusoidal, right? This creates what's called current distortion or total harmonic distortion in the system, and that introduces switching harmonics, which are not good, right?
When you say switching, you mean that is the switching part, or you mean something?
I mean, yes, this switches from AC to DC, but this is a switch mode regulator as well, so this will also affect the current, right? So in an ideal world with a particular resistance here, this is your current. This is what the current's going to look like. If you start drawing current on the load, this current will actually become more shifted, right? And so it may look something like this. For example, this is your pure AC sine wave, and your current becomes harmonically distorted, right? So what power supply companies have done to prevent some of this is that they've introduced, this is again the simplest circuit as a fundamental building block, power factor corrected circuitry, right? And what the power factor correction circuitry will do is it will actually optimize the switching on the front end of the power supply. So the PFE 3000 uses something like this, much more elaborate system. And it will smartly decide when to turn on and how much current to use through this inductor on the front end in order to get a much nicer current profile, right?
It's all MOSFET Q1?
Yes. Or IGBT or equivalent, right? MOSFET or IGBT, fundamentally. So this is how power factor correction works, right? And there's different algorithms to do pulse width modulation and to do it correctly. And this is constantly adapting based on the load that the power supply is actually producing, right? Or outputting. And I think that's it. Special thanks to Google for other picks.
So the reason going to switching power supply is? What's the reason to go?
Switch mode power supplies? So, very good question. Now I need to pulse. That side, okay. So we have this. We have current profile, which may look like that, let's say. So this is V, this is I. This current profile if you look at the Fourier transform, right, so all the harmonics associated with that, right, you're not going to have only 60 hertz, right?
Yeah.
You're going to have a whole bunch of other stuff here,
Yeah.
okay? In the system, when you have these other harmonics, right, you're going to have an AC power source, you're going to have an inductance, right, and then you'll have multiple loads, motors, other things. If you have a lot of these harmonics circulating in this system, if this inductance is not large enough and able to sync those harmonics, they will actually distort the voltage.
Yep.
That voltage distortion will actually affect the rest of your system.
Yeah, true.
So the boat that, in Italy, there was a big cruise ship that went, the problem was they had too many converters on the electrical system, and their harmonics blew up the controlling mechanisms, right? So they didn't have any type of filtering, right? And those harmonics on their electrical system caused the boat to essentially crash, right?
Was
So-
it an Italian-built boat?
We're not pointing fingers.
And you're blaming the captain for that?
It had a lot
Well,
of passion when it's... Yeah, passion, exactly. They were
You know.
passionate thinking.
Yeah. So that's the basic answer, right? Why harmonics are important. Now, power supplies like the PFE 3000 will not actually make a pure sinusoidal, but they get as close to a pure sinusoidal as possible, so that your line frequency is still high at 60 hertz, and then these become rather high frequency and a lot smaller in amplitude. Right, so they push out, so they remove a lot of the potential dangers associated.
The key energies just stay with 60 hertz.
Right. Right. Yeah.
Very good.
Yeah. That was as simple as I could make it.
Cool. That's good. This is sorry. This is before it reaches the rectifier. They're trying to just smooth out the harmonics in the AC way. Or?
Yes. So the PFE 3000. So a typical block diagram, to simplify, will be an AC. They'll have a PFC, so power factor correction circuitry on the front end. They'll have a rectifier on this side, right? They'll have the DC link, and then they'll have the buck converter, right? So the PFE 3000, from a high level, 35,000 foot level, looks like this inside, right? And so back to the question: does it make more sense to have DC grids? Absolutely yes, but there are still some challenges associated with that. And one of the biggest challenges is fault current.
What?
Fault current, right? The advantage of using AC, because your breakers on a DC system become very expensive, right? The current is always flowing. When you connect, two lines together, your DC positive and negative, that current wants to continue to flow, right? Especially if there's inductance in the circuit. Trying to open that short will create a huge arc. The advantage of an AC system, because the voltage always alternates, within 8.6 milliseconds, you're going to go to zero. The current will go to zero, and that will allow you to actually break open the fault, right? So that's the big challenge. DC is definitely by far much more advantageous to use for a grid because of solar panels and wind and all these alternatives.
So they should have like an explosive interlock for like spacecraft.
Explosive.
Right, when they separate on the space shuttle, or not space shuttle, but on the rocket with the modules,
Right.
they just have explosive blocks.
Oh, really?
Yeah, so it could be like the same thing.
I've seen that though at stations where they basically essentially they want to connect to a high voltage line. They basically almost like, I think with pressured air or something, they eject basically the conductor hitting something as quickly as possible so that they wouldn't have an arc go on between when they're trying to connect to it.
Like on the moon missions, because they didn't really have good technology to make sure that it would separate and not like partially separate.
Sure.
Then they'd have explosive mechanisms to like separate off.
But then you can't reset that breaker. You have to go
Yeah,
reset
you have
those
to.
explosives.
Yeah,
right?
you have to.
Or you have a bicycle pump that's resetting a breaker. So you pump in some air.
Yeah.
What if it leaks? Then every so often it disconnects.
Oh, yeah.
Have to repressurize.
Maybe there's a better way.
So another thing that I missed, which wasn't really important, was induction motors. So there's induction motors, synchronous motors, wound rotors, and
We
so
like
forth.
those.
Yeah, induction motors. Was it you that asked me about the brushes? Or somebody asked me about brushes.
I do know there are no brushes.
I did.
On AC, okay. So induction motors don't have brushes anymore. What they have is the windings, the stator windings all the way around, right, on the outside. The rotor internally is like a squirrel cage rotor, what's called. It's a special design of metal and copper that allows for virtual current To
New
be-
company?
Virtual current, which is essentially a result of mutual inductance, right? So you create a field in your primary that will generate a back EMF on your squirrel cage. That will create a secondary magnetic field in the squirrel cage, and that will start tracking the stator magnetic field,
Oh, yeah.
right?
Yeah.
So you don't really need brushes. And the
Right.
advantages of squirrel cages, and this was part of the Tesla invention and the iterations that came later, is that with the squirrel cage, if you actually add some resistance on the squirrel cage, you can actually allow it to speed up to 60 hertz. So the Tesla two-phase motor, you actually had to give it a little spin to start, right?
Yeah.
With three-phase motors today, you just connect them and off to the races, right? So there's a huge inrush current that happens at that starting point, but because the squirrel cage is designed to, based on the frequency and the slip and all these other things, you can actually spin it from a low, from essentially zero, and start spinning it up, right?
And that's why they essentially, I know for like the Tesla, the motor is rated for 150,000 miles, and then the only thing they do is basically the bearings will wear out.
Yeah.
So they have to rebuild the bearings basically, and that's it. There's nothing
Or you
else
can
really.
grease them. You can grease them.
Is that
over
AC
time.
motor or DC motor?
It's AC.
Yeah, it's a synchronous motor, right?
Yeah, and I think they're like sealed, bearings. I'm not sure if we can, if
No, yeah,
if
probably,
people would
yeah.
rebuild them really, or if
Right.
they would just rip them out and put new ones in. But it's a single gear AC motor, and so there's little that can go wrong. I mean, in the motor, there's obviously electronic that can
No, it's nothing. It's very simple design, right?
Yeah, but the electronics obviously need to generate different frequencies to actually have the motor running.
The converter, the power electronics converter.
Yeah. I mean, there's
Yeah.
stuff that can go wrong, but the mechanics itself are probably as simple as it gets.
So if a converter, so it's interesting, right? With power converters, you can get 80,000 hours of operation, right? If it's designed right. So you have appropriate snubber circuits, you're not over-voltaging the IGBTs and all these other things, right? The motor will actually the bearings of the motor will actually go before the converter does, fundamentally.
Yeah, I heard from some guys that were building, converters from DC to AC for like solar panels back into the grid, and they're known to fail after 10 years, like 8 to 10 years. That's like their lifespan. It's basically like everyone does it, and so sometimes they offer an insurance because they know it's going to go bad. And give you a new one after.
It's so DC to AC, because you have to synchronize with the grid and because the voltage levels are so high. There's some design challenges associated with that. So getting everything to last a very long time is difficult, right?
Cool.
So why would Tesla pick AC motor as a...
So Tesla was,
I mean, not the car, not the guy.
oh, the car. So the induction motor is a much more durable motor than the DC. The electronics are more complicated, obviously, but if you get the electronics and control right, the induction motor will last you, order of magnitude longer than a DC motor.
So
right?
how about the torque?
In comparison to DC or just in general? It's about the same, I think, right? It's not necessarily more. It depends. I think DC motors have a little more torque potentially.
Because DC depends also if it's in series wound or parallel, isn't there? Like, depending on how you hook up, basically, if you have a DC motor where you have the outside,
Yeah,
in
you
series
can
with the rotor windings.
Yeah, typically, I think typically you can get more torque out of a DC traction motor, but because of the electronics, because of the density with induction today, you're pretty close, right? You're pretty close, so it's no longer a negative for induction
Yeah.
motors and so on, right?
So three-phase AC motor, or
The Tesla? I
Uh-huh.
believe so, yeah. It's a synchronous.
so if you can put like 5-phase, kind of like V5, V6, kind of or like that.
You can do that.
Your electronics would have to, you have to have enough.
Yeah, yeah,
Okay,
yeah.
more power, right?
Yeah, but you also need more room, right? It's not necessarily more power, so if you design it right, it's all about how your magnetic field is distributed internally, right? You can get much more power by just focusing on reducing the air gap between rotor and stator, rather than trying to go into, multiple poles. Or additional.
I mean, the motor is about this,
Yeah.
and it's a
Two, right? Two, one each side.
No.
Just one.
single one. This thing has
Yeah.
416 horses.
For short durations.
Yeah, the cool, that my German car magazine, they tested it, of course, and they were upset after the 10th full throttle acceleration, 0 to 60, that the actual, motor decided it was getting too warm, and it was
Right.
actually not the same as the first one.
Right.
They're really upset about that, because the BMW doesn't do it, and the VW doesn't do it, but Tesla did it.
Was
So-
the BMW and Volkswagen internal combustion engines?
No,
or
the i3
electrics?
and the e-Golf that you
Alright.
can buy
Or
here.
if you want your motor to melt.
But no, it was just designed probably more conservatively. They limited but they definitely measure the temperature of the motor, and
Sure.
then just throttle when it's too much.
So like Eric is saying, the motor is pretty small on the Tesla, right? For short durations, you can actually put 400 or 500 or even 10 times the amount of power in a motor that it's rated for, because motors are rated for running continuously. So if you have a 100 horsepower motor, right, for 7 or 8 seconds of acceleration, you can put 6, 7, or 1,000 horsepower in this thing, right? Because a lot of current will actually stress the motor. It will but heat is what will kill it, right? So for 6 or 7 seconds, there's thermal resistance ratio that it's not long enough to actually heat up the motor, right? So those are one of the advantages of electric motors.
I've heard that's what they do on missiles.
On which one?
On missiles.
Missiles?
Because the motors don't need to last, so
Yeah.
they put like tiny little motors, but they like supercharge it, and they basically break.
Makes sense, yeah.
Yeah.
Makes sense.
The warranty on these things is short. Yeah.
Makes sense.
Cool.
So, yeah. Hope you learned something.
Yeah,
It's excellent talk. I really liked it.
Looks good.